Welcome back to the Mechanics of Solid lecture series. In this series of videos we're working some examples on simple indeterminate axial systems. And the next example we're going to look at is axial bars connected end-to-end in series. So if you look at this problem, we have three bars connected together in series with internal flange plates. The areas of each bar are given, the length of each bar is given, and the system has internal load of 68 kilonewtons acting to the right at flange B, 125 kilonewtons acting to the left at flange C. We're also given that all members are made of the same material, and I'm going to go ahead and interpret that. What that means for us is that the elastic modulus for each of the bars is equal to the same, so E1 equals E2 equals E3. And then we're asked to find the internal axial forces and draw an axial force diagram. And I'm going to label the internal forces in each bar as F1, F2, F3. Since the loads are given in kilonewtons, I'll solve for the forces in kilonewtons. And again, I want to draw an axial force diagram. Okay, this, as we look at it, is an example of axial members in series. And the textbook teaches a very methodical approach to this type of problem, which we're going to use every time. Okay, if we look at it, we have three unknowns, so we need three equations to solve for those unknowns. And we can get two of those equations from equilibrium. We'll have to get the third from compatibility consideration. And the important thing is what equilibrium equations to draw or to look at. So we could do a cut in bar 1 and do equilibrium at the end, but then we have to introduce another unknown, which is the reaction. So the most direct approach is to do equilibrium of these internal flange plates. So we'll do equilibrium of flange plate B and an equilibrium free body diagram of flange plate C. Okay, so let's start with flange B. Free body diagram of flange B. Just a little plate like that. Okay? I have the internal force in member 1 acting on that flange plate. I'm going to assume it's in tension. That's another thing that the textbook does, is to always assume the force is in tension. You don't have to do that, but it's fairly convenient to do so. So if they're in tension, they're pulling away from the flange plate. F1 acting to the right, F1 acting to the left, F2 acting to the right. And then we also have our 68 kilonewton load. Okay? And our equilibrium equation, based on that free body diagram, we're going to take the sum of the forces in X equal to 0, positive acting to the right, and this is going to be equation 1, negative F1 plus F2 plus 68 kilonewtons equals 0. And I'm just going to leave that alone for now and come back to it. Okay, I also, as I mentioned, want to draw a free body diagram of flange C. And there's my little flange plate. This time I draw F2 acting to the left, still in tension. Now it's pulling on flange plate C. F3 acting to the right, and our load of 125 kilonewtons acting to the left. And my equilibrium equation again is sum of the forces in X equal to 0, positive acting to the right. This is going to be my second equation. I have negative F2 plus F3 minus 125 kilonewtons equals 0. Okay? Now I look at these two equations and both of them have F2 in them. So what I'm going to do for convenience is solve for F1 in terms of F2. So F1 equals F2 plus 68 kilonewtons. Always remember to carry your units all the way through the equations. F3, I'm also going to solve for in terms of F2. F3 equals F2 plus 125 kilonewtons. Okay, so those are two equilibrium equations that we're going to work with. And then, as mentioned, we also need a compatibility equation. Okay, what is our compatibility equation? Some relationship between the internal deformations. And what we know is that if there's a rigid support, the support at D does not move. So that means the sum of all the internal deformations, which is the total deformation at joint D, has to be equal to 0. And I will write that as delta 1 plus delta 2 plus delta 3 equals 0. This is always your compatibility equation. For axial members connected in series, the total deformation is equal to 0. How do we calculate those deformations? Magic equation, FL over AE. I'm going to write that F1 L1 over A1 E1 for member 1 plus F2 L2 over A2 E2 for member 2 plus F3 L3 over A3 E3 for member 3. Set that equal to 0. Now we've got, and that's our third equation, now we've got the setup. That's the hardest part for most students. I recognize here that because E1 equals E2 equals E3, as we said before, I can pull that 1 over E out of the equation, and I'm left with F1 L1 over A1 plus F2 L2 over A2 plus F3 L3 over A3 equals 0. Okay? And basically this 1 over E isn't going to affect the equations anymore. It still equals 0 no matter whether I have the 1 over E there or not, so I'm going to get rid of it. And we will use this as our starting point to continue this example on the next video.